So let's just get started. First of all, Lewis dot structures are also known as simply Lewis structures. A Lewis structure is an illustration depicting the bonds between atoms in a molecule, as well as the lone pairs that exist on those atoms. All of the electrons that are depicted, whether they are bonding electrons or lone pairs, all of the electrons depicted in a molecule will be the valence electrons of each atom. Now, as we're doing Lewis dot structures, I'm primarily going to stick, if not entirely, stick to the main group elements, which was group 1 and 2, group 13 through 18. So let's get into the Lewis dot structures of the atoms of the elements. And as we do this, we're going to talk about really, I'm going to talk about the first 10 atoms of elements, and we're going to discuss the number of valence electrons and then what the Lewis dot structure looks like. So one of the things that I have on here is the group number. The reason I put the group number in there is because if you'll recall before the last exam, when we were talking about valence electrons are the electrons in the highest shell. Yes, we could write out the electron configuration and figure out what the valence electrons are, but we can also look at the last digit of the group number for all of the main group elements. So with hydrogen, hydrogen's in group 1, the last digit is a 1, so it has 1 valence electron. Now, to illustrate a Lewis dot structure of hydrogen, or actually any element, the first thing you do is you write the symbol for that element. So that is our first step. Now, when you write the symbol for the element, you're taking into account any core electrons that the atom has. So the symbol represents not only the identity of the element, but its core electrons. Now we're going to put in the valence electrons. And as we put in the valence electrons, you have to imagine that there is an imaginary square surrounding our element. And what we're going to do is we start out by placing 1 dot on each side of that square, and then we'll come back and pair it up anytime it's needed. So for hydrogen, hydrogen has only 1 valence electron, so it needs only 1 dot. So this would be the Lewis dot structure for hydrogen. Now helium's actually in group 18, but you'll notice my exception to this rule. That is because helium is over with the noble gases, but the number of valence electrons in helium is only 2. So we cannot use the group number in the case of helium, but we can for every other element we come across, just not helium. So helium has 2 valence electrons. So we begin by placing the elemental symbol, and then we add 2 electrons. Now, you can add your electrons where they are here, or we could add it. Come on, wake up, Pim. We could add it so that they are on opposing sides. Whoops. So it could also be written in this format, and both of those are correct. It could also be written where you have the helium and you put the dots here. So in other words, it doesn't matter where you put your dots. It's just you're going to put 1 on each side of the square before we start pairing them. Okay, now let's move on to period 2. We have lithium. Lithium is in group number 1. Being in group number 1, it is going to have 1 valence electron because that's the last digit in that group number. By writing the elemental symbol for lithium, we took care of 1s2. We took care of all the electrons that helium has. So it's kind of like a noble gas configuration to a large extent. where the elemental symbol represents all the electrons that are core electrons. Now we only need to represent our valence electron, which is 1 electron. Beryllium is in group 2. The last digit is a 2, so it has 2 valence electrons. So we're going to place our 2 valence electrons surrounding that beryllium atom. Boron is in group 13. The last digit is a 3, so it has 3 valence electrons. So we can place 1 on each side of our imaginary square. Carbon is in group 14. The last digit is a 4, so it's going to have 4 valence electrons. Nitrogen is in group 15. The last digit is a 5, so it has 5 valence electrons. And at this point, you have enough electrons to actually start pairing your electrons. Now, you'll never put more than 2 electrons on the side of a Lewis dot structure. 2 electrons is the maximum that goes on any one side of the element, because these would be considered a lone pair. So it's always done really in pairs. Oxygen is in group 16. The last digit is 6, so it has 6 valence electrons. And so you can start pairing them up. Fluorine is in group 17. The last digit is 7, so it has 7 valence electrons. So you put 7 dots. And neon is in group 18. The last digit is an 8, so you're going to put 8 valence electrons. The noble gas structures are stable because they have an octet. And we're always going to work towards an octet. Whether we're talking about an ionic compound or whether we're talking about a covalent molecule, our goal is to get our atoms to the nearest octet or to the nearest noble gas configuration. So that is all there is to developing the the Lewis dot structure for an atom of an element. You figure out the number of valence electrons and you put 1 dot around each side and then pair them up. Let's move on to ionic bonds. Ionic bonds contain, ionic compounds contain ionic bonds. And as I've said, I believe on multiple occasions, ionic bonds are simply an electrostatic attraction, basically a magnetic attraction between a positive cation and a negative anion. When those 2 ions come in close proximity, they're going to be attracted to one another. The elements that form cations lose those valence electrons, and those valence electrons are transferred to the element that forms the anion. So the elements that form the anion gain those electrons in order for the anion to have an octet. Now, the only exception to this rule would be hydrogen. Hydrogen's always going to be an oddball. If you were to get a hydride anion, then the maximum number of electrons it can have is 2. The maximum number of electrons hydrogen can ever have is 2. If you ever give me a hydrogen with more than 2 electrons, it will be counted wrong, because as of right now, there's no miracle workers. Now, the number of electrons that can be absorbed by an element to form that anion is going to be dependent upon the spots available before an octet is reached. So the number of electrons we actually can add to an element in the formation of an anion is going to be dependent upon how many spots it has available to it in order to reach an octet. So here in just a moment, we're going to go back and look at our electron dots, our Lewis dot structures for the elements. But I want to give people a minute or two to catch up on writing. Okay, so let's go back to the top and actually look at this last statement and what I mean by this last statement. So we can, let's start with carbon because it's going to be really the first one. So right now, carbon has 4 dots. In order for carbon to get an octet, it has 4 places where it could share an electron. Nitrogen has 3 places to share an electron before it reaches an octet. Oxygen has 2 places it can share an electron before reaching an octet. And your halogens have 1 place before they reach their octet. So in other words, when we make an ionic compound that contains nitride or phosphide, because they're both in group 15, you can guarantee that you're going to get 3 electrons transferred to that element. Anytime we have oxide or sulfide or selenide, you can guarantee that it's going to absorb 2 electrons in order to get to an octet. And anytime you have a halogen that has formed a halide, meaning an anion of the halogen, you can guarantee it's absorbed 1 electron to form that octet. Again, basically all of these elements are trying to reach a noble gas configuration, which has the octet in its valence shell. Okay, so as we start developing the Lewis dot structures of ions, once we make the ions will be placed in brackets with the charges and superscript to the right. Now, most of the time when I write an ionic compound, I really place the brackets around the anion, and I don't worry so much about the cation because it doesn't have any valence electrons left. All it has is its core once it forms that cation. So I usually personally only write the brackets around the anion. However, I noticed when I was looking through the Chem 101 problems that Chem 101 will use the brackets no matter whether it's a cation or an anion. So again, for me, if you look at my optional homework, it's going to be strictly done as around the anion, whereas Chem 101, you'll see it around the cation and the anion. Okay, so we are going to actually get into forming ionic compounds and developing the Lewis dot structure for an ionic compound. So we have sodium and we have chlorine. Sodium is in group number 1. So it has 1 valence electron because that is its outermost electron. That's its valence electron. Chlorine is in group 17. The last digit is a 7. So it's going to have 7 valence electrons. Now, when these 2 elements come in close proximity to one another, the sodium is going to transfer its electron to the chlorine. When that occurs, you have sodium cation because you're down one electron, and you have chloride that now has an octet in its valence shell because that electron from sodium was transferred. So this would be our Cl minus. Now, when these are in close proximity, the way we would write this is we would write it as Na plus, open brackets, Cl, close brackets with a negative charge. Or for Chem 101, it would be written as Na with a plus charge, Cl with its minus charge. Notice that there is no line between the cation and the anion. The reason that there is no line between the cation and the anion is because when you draw a line, you are indicating that the atoms share electrons. So a line between atoms indicates that atoms are sharing electrons. But in an ionic compound, they're not sharing anything. The electrons have been transferred. So that is why you will not find a line between the cation and the anion. Let's look at another example. Let's look at magnesium oxide. So magnesium is in group 2. So it has 2 valence electrons. Oxygen is in group 16. So it has 6 valence electrons. And so we represent their valence electrons with dots. Now, since we are dealing with an ionic compound, the magnesium is going to transfer its electrons to fill the open spaces on oxygen. So you wind up with Mg2 plus because you have lost 2 electrons. And you have your oxygen that has its 6 valence electrons plus the 2 valence electrons that were transferred from the magnesium to form O2 minus. And so that would be the Lewis dot structure for magnesium oxide. Let's look at one more example. Let's look at aluminum sulfide. So in aluminum sulfide, you have 2 aluminums, and aluminum is in group 13, the last digit A3, so you have 3 valence electrons each. And you have 3 sulfurs, which is in group 16, the last digit A6, so it has 6 valence electrons each. Now what happens is that the aluminum is going to, again, it's going to lose its electrons to become a cation. The sulfur here on the right can absorb 2 of those electrons before its octet is reached. The sulfur on the bottom gets 2 electrons before its octet is reached. And the sulfur on the left here gets 2 electrons before its octet is reached. Now, yes, I can draw this in all sorts of ways. I could write it as aluminum 3+, aluminum 3+, with my O2 minus, or I mean my sulfides that have their octets. Again, there is no, you'll notice there's really no rhyme or reason in where I've placed them, just they have to be in close proximity. I could draw it that way, but instead you're going to see me use it this way because it just makes it a little bit more friendly to read. So I tend to use coefficients before the brackets to indicate how many of each there are. Any questions so far? So far, all we've done is talk about Lewis dot structures of the atoms of the elements and how we obtain Lewis dot structures for ionic compounds. Okay. So when I write a Lewis dot structure for an ionic compound, I am indicating what has occurred with the electrons. I am indicating the motion or the transfer of those electrons. But the transfer of electrons is not the main reason why ionic compounds form. The reason anything occurs, the reason any molecule happens, is because of energy. Most of the time it's in the form of heat energy, which we call enthalpy, but sometimes it's in the form of entropy, which is the energy associated with disorder, chaos. Now, let's talk about the energy behind the formation of these ions. I mean, the formation of this ionic compound. You've actually already been introduced to some of the energy associated with an ionic compound. We've already talked about ionization energy. Ionization energy is the energy that is needed to make a cation. We do so in a sequential stepwise formation. So if I want to make a +2 ion, I have to lose 2 electrons in a sequential series. And we talked about how this second loss is higher than the first. In energy. So again, ionization energy describes the energy associated with making the cation in an ionic compound. The electron affinity is the energy associated with making the anion in the compound. And again, this usually is going to occur in a stepwise fashion, meaning we'll make a -1 and then we'll add another electron to make the -2. And we're going to find that while this energy is frequently exothermic, which we represent with a negative sign, meaning energy is given off. This other one tends to be endothermic, which is positive, meaning that energy is absorbed for this process. So it's not, so in other words, with electron affinity, the first process of making an anion with a -1 charge is a favorable process. But this making a -2 is not a favorable process for most of the elements. We will be keeping in mind these ionization energies and these electron affinity energies as we move into the next piece. For an ionic compound to form, the overall energy must be exergonic. Exergonic is a process that gives off energy to the surroundings. Therefore, the overall energy has to have a negative sign. And the reason we give it a negative sign is because the reaction itself is giving off. It's going away. It's being given off to the surroundings. So let's take that sodium chloride I gave you earlier. If I go look up a ionization energy table, the formation of sodium cation takes up 496 kilojoules of energy. The formation of the chloride anion gives off 349 kilojoules of energy. If I add these together, this gives me a positive 147 kilojoules, which means that it is not favorable if I am taking into account only ionization energy and electron affinity. Again, the formation of sodium chloride, if I just take in account ionization energy for the formation of the sodium cation and the electronic affinity for the formation of the chloride anion, and I add those two together, sodium chloride should not form because it gives off a positive value of energy. Now let's talk about magnesium oxide. With magnesium oxide, you have the first ionization energy, which is 738 kilojoules. You have the second ionization energy, which goes ahead and gives us our +2 charge. For our oxygens, you have the first electron affinity. And then notice and for that formation of oxide with a -1 charge, that part's favorable. But when you actually take that -1 charge and convert it into a -2 charge through the second electron affinity, notice that it's positive, which means that process is actually not favorable. And if I add up the energies associated with the formation of the cation and the formation of the anion, this is 2,891 kilojoules, and it is a positive value. So again, it is not favorable if all I am looking at are ionization energies and electron affinities. The reason it is not favorable is because the ionization energy and the electron affinity do not tell all of the story. They talk about the energy needed to make a cation and the energy needed to make an anion. But remember, when this cation and this anion are attracted to one another, when they come together in that electrostatic attraction, they give off energy. And that energy is called the lattice energy. And is actually that electrostatic attraction that is the driving force behind why ionic compounds form. To illustrate this entire story for why an ionic compound forms, we're going to look at sodium chloride and we're going to look at magnesium oxide using a model. This is the formation of sodium chloride. Now, what you will see is, first of all, the sodium was converted to a gas, and that was a positive energy. You will notice that the chlorine molecule, remember chlorine from yesterday is always diatomic when it comes by itself in nature. So we had to take half of that. We had to break that bond. That's a bond energy. And then the sodium itself is a positive value because we're talking about ionization energies, and ionization energies are always positive. So to start, these processes require 725.1 kilojoules of energy to get to this stage. Now, for the chlorine, and again, this is the ionization energy, whereas this is going to be the electron affinity. You will notice that it is a negative value. Now, if I were to stop there, I would have a energy of a positive 376.5 kilojoules. If I were to stop there. But again, you can't stop there because once you make those ions do not exist by themselves. They're going to come together to form an ionic compound, and the lattice energy is going to be the driving force. Now, if you look at the lattice energy, and you add it to the electron affinity, this process has a negative 1,135 kilojoules of energy. If you combine those two, that is where we get the negative 411 kilojoules of energy. And because it is negative, it means that this is an exergonic process. Which is a favorable process. Any questions about the driving force behind ionic compound formation? That lattice energy. Okay, let's look at, I erased you. Oh well. Let's look at the next one. This is magnesium oxide. The first thing that was done is the magnesium was converted from a solid into a gas. And that required a positive 148 kilojoules of energy. Basically, we had to take and we had to melt it and then boil it so that we got into a gas. The next thing we did is we took our oxygen and actually got it from O2 to simply O. This would be a bond dissociation energy. And again, you'll notice it's positive because we're breaking the O2 bond. The next step we did is we took the magnesium and we went with the first ionization energy to form magnesium +1. And that costs us 738 kilojoules of energy. Again, positive because ionization energies are always positive. Then we took that magnesium and made it into magnesium 2. And again, we're talking about a positive, the second ionization energy. And it is again positive. We're having to rip. The reason ionization energies are positive is because we're having to rip an electron away. Now, in the next step, you will notice that O becomes O minus. And that is a favorable process. It cost us negative 141. So that's favorable. And that's the first, what in the dickens? And that's the first electron affinity. But the second electron affinity, where we take O2 minus and O minus and convert it into O2 minus, the second electron affinity, oops, is a positive value. So looking at the left-hand side of this, if you will, the amount of energy expended was 3,243 kilojoules to get to this point where you had the magnesium cation and the oxide anion. It is only because of the lattice energy, which is, if we were to go from top down, it would be a positive, but if we want to go in the opposite direction, this becomes a negative 3845. So it is dependent upon the direction the arrows are currently drawn. Now, when you take that 3243 and the negative 3845, which is the lattice energy, that's where we get the enthalpy for the formation of magnesium oxide at a negative 602. Because it is negative, it is favorable. It will occur, but the only reason it is occurring is because of the lattice energy. Again, the lattice energy is the driving force behind the formation of an ionic compound. Questions? No, you are not going to have to do all this math other than understanding lattice energies are positive. The first electron affinity is negative, but the second one is positive. And then the fact that the driving force is really the lattice energy. That's the entire reason that ionic compounds form. Now, there is a trend in lattice energy. If you look back at sodium chloride, the lattice energy was a negative 787. If you look at magnesium oxide, the lattice energy is a negative 3,845. So magnesium oxide's lattice energy is a lot bigger. So there is a trend in the lattice energy. The most important thing is the higher the charges on the cation and the anion, the higher the lattice energy. So magnesium oxide, because it was a +2 and a -2, would have a higher lattice energy than would sodium chloride with its +1, -1. The second thing, if everything is the same, the charge, if all the charges are the same, then you have to go to the atomic size. Because the smaller the atom, the higher the lattice energy. So again, do part 1 first. If part 1 doesn't help you differentiate everybody, then do part 2. So place the following in order of decreasing lattice energy. Step 1, determine your charges. So it's a +3 -2, +1 -2, +2 -2, +1 -1, +2 -2. Now, since I want it decreasing, I'm going to have the highest lattice energy first to the lowest lattice energy. Again, the highest lattice energy comes with the higher the charges. So in other words, my highest lattice energy here will be the Al2O3 because it has the highest charges. My lowest lattice energy is going to be NaCl because it has the lowest charges. That still leaves us sodium oxide, magnesium oxide, and calcium oxide. The next lowest is going to be the sodium oxide because, again, you've got one that's a +1 charge. Sodium's just a +1. So it would be the next lowest in line. Which leaves us the calcium oxide and the magnesium oxide. In this particular case, both of the charges are identical. Since both of the charges are identical, we have to go to part 2 of my trends and look at the atom size. Magnesium, so the oxygen doesn't matter, it's the magnesium and the calcium. Magnesium is in period 3, calcium's in period 4, because calcium is is further down on the periodic table. That means that our next substance, or the middle one, would be calcium oxide and then magnesium oxide, because magnesium is smaller than calcium. Any questions about putting these in order of decreasing lattice energy? Okay. So I will be breaking you into groups. I really suggest one of you share your screen. It will make it a lot better. It'll make it where you can communicate just like you would in the laboratory. It'll help everybody in the group understand what's going on. So I really do suggest somebody in the group share your screen. But I am going to put you in breakout groups, and you are going to do assignment 1. It's in the practice. It's a practice, and it's Lewis Structure Lab Activity 1. So let me get you into your breakout groups. You will have about 10 minutes to do this particular one. Let's see. And let's go for this. Okay, everyone should be back. So we are going to go ahead and get back into the material. Now we're going to move on to covalent molecules, and we will be spending the remainder of today working on covalent molecules and developing the Lewis structures for covalent molecules. So covalent molecules contain covalent bonds. Covalent bonds arise through the sharing of electrons between 2 atomic nuclei. Now, as we'll learn probably next week, the electrons are not shared evenly necessarily between the 2 atomic nuclei. Now, the question is, why do covalent molecules form? We know that ionic compounds form because of the lattice energy. So why do covalent molecules share their electrons? And the reason is because it lowers the energy. So what I'm about to do is I have a video that I am going to play. So let me stop this broadcasting momentarily. and share my screen with you. And get where I can also see the chat. There we go. Okay, so the very first thing I'm going to do is ask you if you can hear this video. Could you hear that? Or is it just coming to me? No, okay, that's what I was afraid of. Oops. Well, let's see. How am I going to do that? I just have to remember, it's been a long time since I've done this. Okay, I know what I'll do then. Let me go back and go to here. And let's try this again. Can you hear it? No. Anything? Okay, well, then I will go back to what I was doing instead of working through it this way. That's okay. I always have a backup plan. Okay, so that's what my drawing was for, is in case I needed a backup plan. So what we have here is we have the energy. And it is increasing on the y-axis to the north. Now, let's say I have two hydrogen atoms. And those hydrogen atoms are currently separated. What we know is that as those atoms come closer and closer together, we start to see the energy lower. And at some point, those atoms are going to reach what is known as the ideal bond length. And we'll talk about the bond length a little bit more as we go through probably next week. But it reaches the ideal bond length. Basically, the bond length is the distance between nuclei. And now, if we allow those atoms to get too close together, all of a sudden we get this shoot up of energy, because now you have repulsion. Whereas before you had attraction. So we actually, covalent molecules form because of the lowering of energy due to their attraction. Now, as far as what a covalent bond is, so let's take our hydrogen here. Our hydrogen has one proton and one electron, even though those are not the same size. It's not actually, a lot of people will imagine this as a stick between the two nuclei. It's not a stick. Electrons are in constant motion. What is happening when we form a covalent bond is that the electron on one atom is attracted to the protons on an adjacent atom. So in the case of our hydrogen, the electron on the left atom would be attracted to the proton in the right atom, and vice versa. This is what a covalent bond actually is. It is an attraction. And so when we start talking about these atoms coming together, as I illustrated in the graph, they got closer and closer together. The reason they're getting closer and closer together is because of that attraction. And you're going to have what is considered to be an ideal attraction. That is where it is the correct distance apart. And it just happens to cause a lowering energy. Now, this attraction, it actually, just for the record, it doesn't sit at the bottom like I have it currently drawn. The atoms come together, they get closer, and then they go further apart. They get closer. So they're constantly vibrating along this bottom line, where the atoms are just going in and out, in and out. We will talk more about this attraction, which is known as the bond energy. And we will talk more about this bond length later on. But basically what I wanted to let you know is that covalent molecules form because the electrons are shared between two atomic nuclei. And the reason they share between those two atomic nuclei is to minimize the energy in order to get to a negative energy, because this would be 0. So this would be a negative energy, and this would be a positive energy. And so they're trying to get to the negative energy that's given off when they come together. So what we're going to do is we're really going to get into our covalent bonds. We are going to start by developing some covalent bonds, just using some simple Lewis dot structures of the atoms. After that, I am going to move on, and we are actually going to start really using that sheet I gave you yesterday in class that demonstrated or it basically gave you instructions for developing the Lewis structure of any molecule, not just something very simple like we're about to do with the Lewis dot structures of the atoms. So with hydrogen, it has 2 hydrogen atoms. Hydrogen being in group 1 means that it has 1 valence electron each. Those electrons are shared between the 2 atomic nuclei. Now, what this sharing does is basically the right-hand atom sees that believes that the 2 electrons belong to it, and the left-hand atom also views that those 2 electrons belong to it. So now, why is this important? The reason it is important is because hydrogen wants 2 electrons in order to reach a noble gas configuration. In this particular case, helium. So it wants those two electrons, and this is one way it can get it is through the sharing of electrons between the two atomic nuclei. Now, we don't typically write the dots between atoms. Instead, we will write a line. That line is referred to as a single bond, and it literally means that there are two electrons shared between the two atomic nuclei. Hydrogen is the only atom that will get two electrons. Everybody else, well, no, boron doesn't mind having only 6 electrons. So hydrogen gets 2, boron gets 6. Everybody else that is a non-metal or metalloid better have 8. So let's look at oxygen using the same lens that we did with the hydrogen. So you have oxygen, you have 2 of them. Oxygen is in group 16, the last digit is a 6, so it has 6 valence electrons. That is true for both of our oxygen atoms. Now, if oxygen shares a pair of electrons between the two atomic nuclei, this structure evolves. The right-hand oxygen says, okay, I have 7 valence electrons. The left-hand oxygen says I have 7 valence electrons. But again, hydrogen needs 2, boron needs 6. Everybody else that is a non-metal or metalloid better have 8, called the octet rule. So our oxygen atoms are going to share another pair of electrons between the two atomic nuclei. And this structure evolves. Now, once this structure evolves, the right-hand oxygen views the electrons between the two oxygen atoms as belonging to it. So it says, okay, I have 8 valence electrons. That means that it is content because it has its octet. And the left-hand oxygen also says, okay, I got 8 valence electrons. So it is also content because it has an octet. Now, we don't usually illustrate this using dots. Again, we don't illustrate bonds between atoms using dots. So it would be more commonly written in this format. The double line is referred to as a double bond, meaning that there are 4 electrons shared between the two atomic nuclei. Let's look at nitrogen. Nitrogen is in group 15. The last digit is a 5, so it has 5 valence electrons. Nitrogen starts out by sharing a pair of electrons. When it does so, this is the structure that evolves. The right-hand nitrogen says, okay, I have 6 valence electrons, and the left-hand nitrogen says, I have 6 valence electrons. Neither one is happy at this point. because they need an octet. So we're going to share another pair of electrons between the atomic nuclei. When we do so, the right-hand oxygen views all of the electrons shared as belonging to it. Well, that's 7 valence electrons. And the right-hand, or the other nitrogen, also views it as having 7 valence electrons. Again, not happy, because only hydrogen and boron can have anything less than 8. So our nitrogen is going to share, maybe. Our nitrogen is going to share one more pair of electrons. When it shares that third pair of electrons, the right-hand nitrogen sees itself as having 8 valence electrons. The left-hand nitrogen sees itself as having 8 valence electrons. So they are both very, very happy now because they have their octet. Now, we don't usually illustrate it in this format. Instead, we use lines to represent a pair of electrons. So we have 3 pairs of electrons shared, so we use 3 lines. This is called a triple bond. When you have the 3 lines, and it means that there are 6 electrons shared between the 2 atomic nuclei. So in covalent molecules, you can have single bonds, which is just 2. You can have double bonds, which is 4. And you can have triple bonds, which is a matter of 6 electrons that are shared between atomic nuclei. Now, this method that I've used works for period 2 elements. It does not work for period 3 on necessarily. It is for this reason that it is better to use the rules that are outlined in that packet that I passed out yesterday in class. In order to develop your Lewis dot structure. So that is what we're going to do the rest of this time. We're going to begin with water. Water has 2 hydrogen atoms, and it has 1 oxygen atom. Hydrogen is in group 1. Last digit is a 1, so it has 1 valence electron. Oxygen is in group 16. The last digit is 6, so it has 6 valence electrons. 2 hydrogens, each with 1 valence electrons, means that the hydrogens contribute 2 electrons to the overall structure. And the oxygen contributes 6 electrons to the overall structure. So we have 8 electrons to distribute throughout our molecule. This is step number 1, where you simply add up the total valence electrons. The next step is to write the skeletal structure. Typically, the skeletal structure will have the first element in the formula listed as the central atom and the other elements listed as terminal atoms. However, if the first element listed is hydrogen, then you move to the second element because hydrogen must always be a terminal atom. So since the first element was hydrogen, we are moving to the second element, which is oxygen, and we are going to place our hydrogens around that oxygen. Now we have to distribute the electrons amongst our atoms. And we want to make sure that each atom in the molecule gets an octet, with hydrogen only needing 2 and boron needing a maximum of 6, or it has to have at least 6. So we start by drawing a single bond between the external atoms, the terminal atoms, and the central atom. For each bond I draw, I'm going to subtract 2 electrons because remember, each one of these lines represents 2 valence electrons. So I have 2 lines times 2 valence electrons, meaning I've used up 4 electrons in the bond. And I still have 4 valence electrons to go. You always start by giving your terminal elements an octet. But hydrogen already has an octet because it only needs 2, and it has 2 because it views the electrons in that bond as belonging to it. So it already has 2. So we don't need any more electrons for our terminal atoms. Once you've given your terminal atoms an octet, if electrons remain, they go on to the central atom in pairs. So we have 4 electrons remaining, so we're going to place them on the central atom in pairs. And that gives us 0. When you hit 0, folks, you can skip to step 5 and check, does everybody have an octet? Your hydrogens have their octet because they only need 2. Your oxygen has its octet because it has 8 valence electrons. So yes, every element has an octet. So in that particular case, that means we are done forming the Lewis dot structure for water. So let's move on to HCN. We have 1 hydrogen, 1 carbon, and 1 nitrogen. Hydrogen is in group 1, it has 1 valence electron. Carbon's in group 14, the last digit of 4, so it has 4 valence electrons. And nitrogen is in group 15, the last digit of 5, so it has 5 valence electrons. So the hydrogen contributes 1, the carbon contributes 4, and the nitrogen contributes 5 for a total of 10 valence electrons to distribute around our molecule. The next thing we need to do is write the skeletal structure. Again, there are 2 different things here. Number 1, again, hydrogen must be terminal. And number 2, which I always use this phrase, Carbon is always, and I do mean always, the center of attention. And I use that because CNC. So the carbon is going to be our central atom around which we'll place the hydrogen and the nitrogen. Now we've got to distribute our electrons among the atoms. The first thing we need to do is draw a single bond between our terminal atoms and our central atom. And we subtract 2 for each bond we drew. So we drew 2 bonds, 2 times 2 is 4. So we're going to subtract out 4 valence electrons due to our bonds. That still leaves us 6 valence electrons to distribute. The next step says to give your terminal atoms an octet. Hydrogen has its octet. It only needs 2. So we are going to start by giving our nitrogen an octet. Currently, nitrogen has 2 because there are 2 in the bond. So we're going to add an additional 6 electrons to nitrogen. And we hit 0. When you hit 0, you skip to step 5 and ask, does every atom have an octet? If the answer, and so our hydrogen has its octet, it has 2 valence electrons. Our nitrogen has an octet, it has 8 valence electrons, but our carbon currently only has 4 valence electrons. Carbon must have 8. So you go back to step 4. If atoms lack an octet, you start making multiple bonds. So we're going to bring in a whole pair of electrons from that nitrogen. And when we do so, we get this structure. Anytime you alter the structure, you check, does everybody have its octet? Your hydrogen still has 2 valence electrons because there are 2 electrons in that single bond. The nitrogen still has 8 valence electrons because there are 4 electrons in dots and 4 electrons within the double bond. But your carbon currently only has 6 valence electrons. There are 4 within the double bond and 2 within the single bond. So carbon is still not happy. So since carbon is still not happy, we need to share another pair of electrons. And the structure that evolves is this structure. Anytime you alter the structure, you say, does everybody have an octet? Your hydrogen has an octet. It has 2 valence electrons. Your nitrogen has an octet. It has 2 electrons in the dot, and it has 6 electrons in the triple bond. So it has 8 total electrons. And now your carbon also has 8 total electrons, 6 within the triple bond and 2 within the single bond. So now the carbon is happy and everybody is happy. And so that is your Lewis structure for hydrogen cyanide. So some key things I wanted to point out. Number 1, when sharing electrons, the terminal atom always brings in a pair of electrons. The second thing I want you to note is when I hit 0 over here, when I hit 0, you notice that I did not add any more dots or bonds unless I manipulated what was there.
So once you make, once you hit 0, all you can do is manipulate what you have. You cannot just miraculously get electrons from somewhere. You've got to only manipulate what you have. So CCO4, I have 1 carbon, 4 chlorines. Carbon is in group 14, last digit of 4, so it has 4 valence electrons. Chlorine is in group 17, the last digit of 7, for 7 valence electrons. The carbon contributes 4 and the chlorines contribute 28. Adding that together, that is 32 electrons. Carbon is always the center of attention around which we'll place everybody else. You then draw a single bond between the terminal atoms and the central atom. And you subtract 2 for each bond you draw. We drew 4 bonds, 4 times 2 is 8, so we'll subtract 8 electrons due to our bonds. That still gives us 24 electrons to distribute. Once you've drawn single bonds between all of the atoms, you distribute the remaining electrons to the terminal atoms. So I'm going to give, in order for chlorine to get an octet, it needed 6 more because it already had 2 in the bond, so it needed 6 more to get an octet. That is true for each of our chlorine atoms. For the chlorines to have an octet, they need 6 additional electrons. Now, in giving our external atoms an octet, we used up the remaining 24 electrons and we hit 0. When you hit 0, you see that your question is, does everybody have an octet? All of your chlorines have 8 valence electrons because they have 6 in the lone pairs and 2 in the shared bond. Your carbon also at this point has 8 valence electrons because it has 4 shared bonds of 2 electrons each. So at this point, this molecule is content. So carbon tetrachloride has the carbon single bonded to 4 chlorines. Okay, so let's move on to CH2Cl2. We have 1 carbon, 2 hydrogens, and 2 chlorines. Carbon's in group 14, last digit of 4, hydrogen in group 1, last digit of 1, and chlorine in group 17, last digit of 7. So the carbon contributes 4, the hydrogens contribute 2, and the 2 chlorines contribute 14, for a total of 20 valence electrons to be distributed throughout our molecule. Carbon is always the center of attention. Whoops, gave it too many. So we're going to put the carbon in the center with all the other atoms around it. We draw a bond between the terminal atoms and the central atom. For each bond you draw, you subtract out 2 electrons. We drew 4 bonds, 4 times 2 is 8. So we're going to subtract out 8 electrons due to our bonds, leaving us 12 to go. The next thing you do is give your terminal atoms an octet. Hydrogen already has an octet. It has 2 valence electrons in its in that shared pair. Chlorine currently only has 2 valence electrons in the shared pair. In order for chlorine to get a full octet, it needs 6 additional electrons. So 6 electrons plus the 2 in the bond gives it 8 valence electrons. And that is true for both of our chlorines. In giving our 2 chlorine atoms their octet, we use up an additional 12 electrons. And we hit 0. Anytime you hit 0, you see, does everybody have an octet? Well, we've already decided hydrogen and chlorine do. The question is, does carbon? And the answer is yes. Carbon does have an octet because it has 8 valence electrons, because there are 2 electrons in each of those bonds that it shares. There's 4 bonds, 4 times 2 is 8. So yes, this is the structure for dichloromethane. Let's do one more. I think it's one more, yep. Before we go back to Chem 101 and do another set. This one is tougher. This one is tougher because you have multiple central atoms. How do I know I have multiple central atoms? The maximum number of bonds a carbon will get is 4. Carbon, whoops. Well, carbon will always get 4 bonds. That's the maximum. That it can have. It can't have 5, it can't have 6. It cannot go over 4. So the fact that there's 5 hydrogens and a nitrogen tells me that I've got multiple central atoms, because I have more than 4 atoms, and carbon can't go over 4. Now, this is what is referred to as a structural formula. It is telling you how each thing is bonded. Now, before we get into taking that structural formula and converting it into the Lewis-Dot structure, let's start by doing the same thing though. Let's calculate our number of electrons. We have 1 carbon, we have 5 hydrogens, and we have 1 nitrogen. Carbon has 4 valence electrons, hydrogen 1, and nitrogen 5. So the carbon contributes 4 to the overall structure, the hydrogens contribute 5 to the overall structure, and the nitrogen also contributes 5 for a total of 14 valence electrons. Now we're going to take this structural formula and start to convert it into the Lewis-Dot structure. You are literally going to read this thing. 1 carbon and attach it to 3 hydrogens, just like it said in the formula. The carbon is attached to 3 hydrogens. Now, carbon must always have 4 bonds. So the carbon is then attached to the nitrogen. So in other words, I'm reading this in order. You cannot have more than 4. So those other 2 hydrogens cannot be on carbon. And hydrogen is always terminal. So you can't have a hydrogen, it can't be attached to a hydrogen. So those wind up attached to the nitrogen. So literally, I'm taking the formula and the structural formula, and I'm going to convert it into a Lewis-Dot structure. And you'll notice as I went from the structural formula to the lines, the bonds, I put a bond in between each atom as I went. So we have 1, 2, 3, 4, 5, 6 bonds. 6 times 2 is 12 electrons. So we will subtract out 12 electrons due to our bonds, leaving us 2 valence electrons left to go. Now we got to figure out where to put it. Where do we put those electrons? So hydrogen already has 2 valence electrons. That is true for all of the hydrogens. There is a bond. So there is 2 electrons that are being shared. So the hydrogens are all happy. Our carbon has 8 valence electrons because it has 4 bonds with 2 electrons each. So that must mean I need something for nitrogen, because right now nitrogen only has 6 valence electrons. So those other 2 electrons are going to go on our nitrogen so that we wind up with 8 valence electrons on the nitrogen. And we hit 0. And because I had to count as I went, all of our elements have an octet. So this is the structure for what it, and I don't expect you to name this, so don't worry about it, but this compound is called methylamine. You'll learn about that more when you get to organic. Any questions? I want to point something out to you. If you flip to page 3 of the document I gave you yesterday, you will see a periodic table that tells you the preferred number of bonds for each element. You will notice hydrogen always gets 1. That's its only exception, the only thing. If you look at where carbon is, it's gonna get 4. And if you look where nitrogen is, it's gonna get 3. There are only a few exceptions with respect to nitrogen. And I've given you those few exceptions at the bottom of the page, which include the azide anion, the ammonium ion, and dinitrogen monoxide. But otherwise, I believe all nitrogens will get 3 unless they are charged. Any questions? Okay, I am going to send you to a breakout room so that you can do set 2. Let's